So, as an introduction, um, blockchain-based solutions are usually described referring to five main layers, including infrastructure, data layer, network layer, consensus layer, and application layer. The first three layers are usually constructed and maintained by non-blockchain practitioners, yet they need to be defined according to the protocols that are used in the consensus layer and the application layer, meaning that they need to be constructed and maintained by those non-blockchain practitioners in a way that they would provide the proper infrastructure and container for the protocols and mechanisms that are suitable for the application layer. For example, we need to have a peer-to-peer network in the network layer, and we need to define the proper cryptography methods in the data layer. We might need a trusted third party for a permissioned application or a trusted execution environment for example, if we need to use the proof of elapsed time consensus algorithm. So the ledger can be defined referring to the required security level of the system. It might be linear, it might be directed acyclic graph, etc., etc. Until the year 2009, we only had one model to guarantee the security of the distributed system, which is the BFT model. Now, this approach tolerates at most a third of the network nodes to be malicious or faulty. But however, blockchain technology introduced by Nakamoto or Satoshi Nakamoto in 2009 provides higher tolerance for up to 50% of the nodes. Now, this mechanism consumes a lot of energy and has low throughput compared to centralized solutions, which triggered the research community to propose several alternatives, such as the proof of stake, proof of authority, proof of elapsed time, etc. There are at least 40 alternative consensus algorithms that I know of, and the application layer consists the definitions and aims of the system. So according to all of these, different layers can be set to fulfill the application requirements in order to provide the needed service. Regarding the advantages and disadvantages of blockchain technology in general, we can find several advantages in the literature proven experimentally and theoretically. Integrating blockchain with other technology provide reduced congestion due to the distributed nature of the network and also higher trust and reliability levels of the system since there's no controlling trusted third party or server. The immutability criterion is sometimes described as a disadvantage since it depends on the data saved on chain. So if the data includes private data depending on the application design, then such system is considered non-GDPR compliant because data cannot be deleted once saved on chain. However, if the application is well defined, then the immutability of the blockchain provides higher integrity of the system since a full history of data can be retrieved easily, and thus we can consider this as an advantage of the blockchain. Fog computing technology, we usually define it as the extension of the cloud computing at the edge of the network. Service models usually provided by the clouds include infrastructure as a service, platform as a service, and software as a service to perform storage, communication, and computation services. Now, the fog is conceptually a distributed macro cloud platform closer to end users or to the end user layer to provide cloud services, which provides these services with lower latency and higher security. Now, different fog integration architectures were proposed in the literature, but all of these agree on one criteria that the fog layer provides the cloud services closer to end users. Whenever we integrate blockchain with a cloud or fog enabled solution, we can state that the cloud is now providing blockchain as a service model, where blockchain computations and applications can be deployed in the cloud or the fog. And here we take the advantages of both technologies. We take the advantage of low latency of the fog computing, and at the same time, we take the advantage of security and integrity of the blockchain system. Now let's talk about the digital identity. Um, Generally speaking, defining what an identity is considered an open issue in computer science. Like, is it your IP? Is it your name? Is it your photo, your MAC address, etc.? How to define a good or a bad identity, and what is the level of uniqueness a given identity provides? All of these are questions to be answered whenever we have to use a multi-party computer system. And because of that, we need to identify maybe a standard for identity when we talk about the utilization of data uh, or verification of data within the framework of the internet. Sorry. So we can identify actually three main types of digital identity models. First, we have the centralized model, where users need to register to different platforms and possibly identify themselves differently. Each platform maintains its own database and perhaps its own identification criteria standards. In order to register users in all needed platforms, the user needs to individually deal with every platform and, provide private data according to the requirements of the platform itself. The second type is the federated identity model, where less known platforms delegate their right to obtain private users' data to another, like more trusted platform. So we have an example here of a website that asks you to register either by providing your data, or you can connect with either Facebook, Twitter, Google, etc. So you don't have to go through the hassle of registering as a new account. Now, this model eases the process of registering on different platforms, but still force or uh, uh, deal with several challenges, such as the privacy concerns and perhaps yet lower level of centralization. However, since identification criteria are not standardized for all service providers, the platform who delegates decides which platform to trust instead of the user. So it's kind of more easier compared to the centralized identity model, but still it has some its own disadvantages. The third model of identity is the one we do study a lot in the context of blockchain, which is the SSI, or what we call self-sovereign identity. So here we have a unified database for all platforms maintained by different service providers, but using one standard identification framework. The smartness in this model can be seen in separation of roles for elements of the system. The issuer, for example, is the element that issues verifiable data, who initially registered itself with a unique identifier at the public distributed database, or what we usually use blockchain for securing it. Now, the owner or the holder of this verifiable data requests it and can verify it using the same unified identity database, since it is publicly accessible for all users. And the verifier role can be played by any element of the system to verify whether a given data is valid or invalid. Now, in this context, the validity means the generation of the data was performed by the issuer itself, not any other element. So this is the basic validity criteria, but you can add as many validity criteria as you need according to the application model, of course.